Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain from Jivaji University Gwalior. Today we are going to discuss about a module Thermoanalytical Chemistry Part 1 under paper Fundamentals of Analytical Chemistry. As the name implies, it is simply the effect of temperature. Thermoanalytical effect of temperature. We are analyzing. We are analyzing effect of temperature. The term thermal analysis incorporates those techniques in which some physical parameters of the system is determined and or recorded as a function of temperature. On the one side, we shall increase the temperature and we shall record the physical parameter. DTA, one of the thermal techniques, is differential thermal analysis, allows the detection of every physical or chemical change, whether or not it is accompanied by change in weight. Other thing, differential scanning calorimetry, another thermal analytical technique, DSC, is a thermal method whereby the energy necessary to establish a zero temperature difference between a substance and a reference material is recorded as a function of temperature or time when both are heated or cooled at a predetermined rate. When matter is heated, it undergoes certain physical and chemical changes. These physical and chemical changes take place over a wide temperature range. Means when temperature is ranges, as in the case of if you have seen boiling of water, water is boiling, then certain changes takes place at 100 degree or so it is being converted into vapor. So, and if it is cooled, it is converted into ice. So this is a temperature dependent. With temperature, things are changing, state is changing. So similarly, physical and chemical change take place over a wide temperature range. Physical and chemical changes taking place. Physical changes such as melting or boiling may occur at widely varying temperatures depending on the materials involved. Chemical changes such as decomposition or reaction may also take place at very different temperatures. So what are physical changes? As I told you that it is the conversion of water into ice or vapor, physical changes, various other physical changes may take place, but side by side, various chemical reactions take place. In many cases, the compound may break, compound may decompose, as in the case of calcium carbonate. At particular temperature, carbon dioxide gas is released and it forms calcium oxide. So, such type of decompositions may occur. The physical and chemical changes a sample undergoes when heated are characteristic of the material being examined, and these are the characteristics for particular substances. As boiling point is a characteristic of water, boiling point, melting point, characteristic, boiling point of benzene is characteristic. You can find out if certain have boiling point 100, then you can say that the given substance may be water. So these are the characteristics for that substance. By measuring the temperature at which such reactions occur and the heat involved in the reaction, we can characterize the compounds present in the material on the basis of thermal effects. The physical and chemical changes that take place when an unknown sample is heated provide us the information that enable us to identify the material on the basis of effect of heat, on the basis of thermal effect, we may identify the unknown compound. These changes also indicate the temperature at which the material in question ceases to be stable under normal conditions. This information is very useful to industrial chemists such as those who make varnish and paints, since it allows them to predict the service lifetime of such compounds. During the last few years, the method of thermal analysis have been widely accepted in analytical chemistry. The term thermal analysis incorporates those techniques in which some physical parameters of the system is determined or recorded as a function of temperature. The various techniques of thermal analysis are summarized in Table 1. Thermoanalytical techniques are a group of techniques. It is a group of around 10 to 15 techniques which are based upon the instrument employed for measurement and also the parameter which we are studying. In thermal, all these 10 or 15 techniques, which are thermal techniques, the basic thing is the same, that we are applying the heat. We are heating the material, we are heating the substance, the observing the changes caused due to the effect of heat, thermal effect. We are changing. So first type of technique here is thermogravimetry. As the name implies, it is the gravimetry, taking the weight. So we take here the weight on heating, on thermogravimetry. On heating, we have a very sophisticated technique, sophisticated balance, thermobalance. On thermobalance, every time we note the change in temperature, change in mass with temperature, because when we will heat, mass will decrease. Some water vapor may evaporate, some decomposition may take place. So every time after application of temperature, after increasing the temperature or thermal effect, we will measure in the form of mass. Mass versus temperature, a plot will be drawn between mass versus temperature. Another type of thermal analysis, thermoanalytical technique is derivative thermogravimetry. Derivative thermogravimetry, which is also called as DTG in short. Here again, we will note the change in mass with the temperature, and here thermobalance is again instrument is thermobalance, which is will utilize for measure or taking the weight of the substance, and plot will be in between the different mass, but mass temperature versus mass upon versus temperature. A plot will draw here, as in the case of earlier, a plot was mass versus temperature or time. Here also it is the differential of mass which we will take here versus temperature. Another third technique is differential thermal analysis, that is the DTA. Here the apparatus used is the differential thermal. So complete apparatus will be used, DTA apparatus will be used, and here it is the plot of delta T versus temperature. We will take a plot, and this is a very important technique we will measure here. These techniques are particularly useful in studies of polymers, polymer chemistry. These techniques are widely used in polymer chemistry, in coordination compounds, in complex formation. These techniques are very widely used. Next type of thermoanalytical techniques is differential thermal analysis. DSC. This is not differential thermal analysis. It is differential scanning calorimetry. Next technique is differential scanning calorimetry, and here the instrument which we will use for measurement is a calorimeter. Calorimeter, scanning calorimetry. So we will use here a calorimeter for the measurement. That instrument will be used. Another will be the thermometric titrimetry. Thermometric titrimetry, a type of titration, and here again a calorimeter will be used for the measurement of the things. Another type of technique which has been developed is a dynamic reflectance spectroscopy. Here a spectrophotometer is used for the measurement. Next technique is evolved gas detection. Whatever gas is evolved, that is measured. Evolved gas detection, represented as EGD. Thermal conductivity cell. Here thermal conductivity cell is the instrument, the measurement device by which we will measure is the thermal conductivity cell. Based upon the measurement basis is the evolved gas detection is made. Another type of technique, thermal technique, division of subdivision of thermal technique is thermomechanical analysis. thermomechanical analysis is done, and the instrument is used here is dialometer. Dialometer is used, and the parameter which is to be used is volume of length. Volume of length is taken versus temperature is recorded. So these are the different techniques. One by one modifications are coming there. Next one is the electrical conductivity. Here electrometer or budget is used, and current is measured, and a plot is between uh, current or current versus temperature is a plot is drawn. Another type of thermoanalytical technique is emanation thermal analysis, represented as ETA. Here again, the radioactivity is measured. Radioactivity is measured with respect to temperature. Thermal events are usually studied by recording the change in thermal property as the temperature is varied to give a thermal analysis curve or thermogram. According to analytical chemistry, any analytical instrumental technique is regarded as a thermal analysis method if the physical parameter is measured as a function of temperature. Protonuclear magnetic resonance, electron spin resonance, electron diffraction, X-ray diffraction, mass spectroscopy, UV visible, and IR spectrophotometry and thermal methods are some of the methods according to this definition. It is important to mention here that single thermal analysis method does not provide complete information of a system. However, additional information may be provided by other thermal methods if required. According to Van Landet, four thermal methods are most important should be considered. Differential thermal analysis (DTA), differential scanning calorimetry (DSC), thermogravimetric methods (TGA), derivative thermogravimetry (DTG). We shall study one by one these techniques. First is differential thermal analysis. This technique is simple as it involves the technique of recording the difference in temperature between a substance and a reference material against either time or temperature, as the two specimens are subjected to identical temperature regimes in an environment heated or cooled at a controlled rate. Thus, a differential thermogram consists of a record of the difference in sample and reference temperature, that is, differential temperature dt plotted as a function of time t, sample temperature Ts, reference temperature Tr, or furnace temperature Tf. An ideal DTA curve is shown in figure 1, in which there is an exothermic peak and an endothermic peak. Both the shape and size of the peak may furnish good information about the nature of the test sample. Generally, sharp endothermic peaks give ideas of changes in crystallinity or fusion processes, whereas broad endotherms signify dehydration reactions. In most of the cases, physical changes give rise to endothermic curves, whereas chemical reactions give rise to exothermic peaks. The origin of the temperature difference in the sample, that is delta T, lies in the energy difference between the product and the reactant or between the two phases of a substance. This energy difference is manifested as enthalpic changes, either exothermic or endothermic. The DTA curve would be parallel to the temperature axis till the sample undergoes any physical and chemical change of state. DTA allows the detection of every physical or chemical change, whether or not it is accompanied by a change in weight. Factors affecting the DTA curve. The DTA curve is affected by a larger number of factors than TG curve. The special influences on DTA curve will be considered here. The various factors affecting DTA curve are environmental factors, instrumental factors, and sample factors. Environmental factor. The DTA technique is more sensitive to the gaseous environment around the sample than the thermogravimetry technique. In DTA, it studies two types of gaseous atmosphere, are used: A static gaseous atmosphere, B. A dynamic gaseous atmosphere. A static gaseous atmosphere is difficult to reproduce because the atmosphere surrounding the sample is changing in concentration chemically due to evolved gases and physically due to convection current. Therefore, the studies in a static gaseous environment are imprecise. Results obtained in dynamic atmosphere, where the gases are swept past the sample in a controlled way, are reliable and reproducible. The swept gases can be either inert or reactive. Instrumental factors: the geometry and the material used in the fabrication of the sample holder affect the resolution, shape, and size of the DTA peak. If the sample holders are made from materials of high thermal conductivity, that is, metals, sharp exothermic peaks, but relatively flat endothermic peaks are obtained. Differential temperature sensing devices. Generally, heats of transistors are much less as compared to the heats of reactions. If the wires used in temperature sensing devices are much thick, more distortion of the peak height and peak temperatures may take place. However, thinner wires are used, lesser distortion in peak height and peak temperatures may take place. Furnace characteristics. The type of winding shows a direct effect on the DTA curve. If the winding used in furnace is not uniform, the baseline is changed. This type of effect is generally seen in hand-wound furnaces. Selecting the temperature programmer controller is very important because a constant heating rate is required in DTA. Thermal regime. The heating rate has a great influence on the DTA curve. Higher the heating rate, higher the peak temperature, and sharper the peaks with greater intensity. Generally, heating rates 10 to 20 degree per minute are employed. Physical. Heat capacity remains constant with progress of the reaction, but this is changing with the progress of the reaction. The effect of particle size is related to the effects of packing density and overall thermal conductivity of the sample. In general, following inferences are drawn from the variation in size of the particle. Particle sizes changes peak area. Particle size also influences the peak temperature. Particle size also changes the completion temperature. Chemical changes. The chemical reactivity of the sample holder, thermocouple material, the ambient gaseous environment, and added diluents greatly alter the DTA peaks. Another important area to be studied is the instrumentation for DTA apparatus. As a large number of different types of instruments are available for DTA studies, DTA apparatus shown schematically in figure 2 has various components which include furnace, sample holder, DC amplifier, differential thermal detector, furnace temperature programmer, recorder, control equipment. Applications of DTA. Some applications of DTA which are of particular interest to chemists include study of heat of reaction, specific heat, thermal diffusivity, and the various applications which are of interest to analytical chemists are identification of substance. The DTA curve for two substances are not identical, therefore, they serve as fingerprints for various substances. Identification of products. When a substance reacts with another substance, the products are identified by their specific DTA curves. As melting points can be easily determined by DTA, it means that this technique can be used as a direct check of the purity of the compound. Another application is in quantitative analysis. The area of DTA peak is proportional to the total heat of reaction and hence to the weight of the sample. Therefore, quantitative analysis is possible with the help of standard curves of peak areas versus weight as shown in figure and 3 and 4. of polymer analysis. Applications to inorganic chemistry. DTA technique has been used to study the thermal stability of a large number of inorganic complexes. DTA curves are more helpful in the identification of intermediate compounds. DTA technique has been used to study oxalates, metal-amine complexes, carbonates, and oxides. It has also been used to study the oxides of uranium and plutonium. Applications to organic chemistry. DTA investigations have been carried to help identification, purity determination, and quantitative analysis, including the evolution of kinetic parameters of polymers, explosives, pharmaceuticals, oils, fats, and other organic chemicals. Another thermal technique we shall study in this module is differential scanning calorimetry, commonly known as DSC. It is a thermal method whereby the energy necessary to establish a zero temperature difference between a substance and a reference material is recorded as a function of temperature or time when both are heated or cooled at a predetermined rate. The DSC curve is recorded with charred epsica indicating the transition temperature. The area of peak measures the total energy transfer to or from the sample. The relative advantages of the DSC techniques over DTA techniques are summarized in Table 2. From Table 2, it is clear that we can take a smaller size in DSC in comparison to DTA. In DSC, we can take 2 to 10 milligram of the sample, whereas in case of DTA, minimum amount of the sample to be taken is 20 milligram. The sensitivity of measurement of heat of transition in DSC is few joule per mole, whereas in DTA it is zero point 0.5 kilojoule per mole, a very difference, and it goes in favor of DSC. Heating and cooling cycles, programmed heating and cooling possible in case of DSC, whereas generally programmed heating is possible in DTA, but in case of DSC, both heating and cooling can be programmed. Second order phase transition, it can be observed with a sample size of 200 milligram, but in DTA it cannot be observed, so it is a superior technique in comparison to the DTA. Specific heat measurement, in case of DSC it is very accurate, whereas in case of DTA it is not accurate. A block diagram of the instrument used for DSC analysis is shown schematically in figure 5. The instrument works on the temperature control of two similar specimen holders in the specimen holder assembly. In its left half, there is a circuit for differential temperature control, while in its right half, there is a circuit for average temperature control. The average temperature control circuit and electrical signal, which is proportional to the dialed temperature of the sample and reference holders, is generated through the programmer. By DSC, one may analyze liquids and solids in the form of powder, crystals, granules, or foil. An inert material like alumina is generally used as reference material. An empty pint with lid is also used. Environment. Generally, DSC measurements are carried out in gas environment. The optimum rate recommended for flowing gas is 20 to 30 milliliter per minute. Various factors that will affect the DSC curve. DSC curves as given in Figure 6. The shape of the sample has little effect on the quantitative aspect of DSC but has more effect on quantitative analysis. About zero point 0.5 to 10 milligram is usually sufficient. Smaller samples enable faster scanning, give better shaped peaks with good resolution, and provide better contact with the gaseous environment. On the other hand, with large samples, smaller heats of transitions may be measured with greater precision. In principle, like DTA, DSC involves the heating of the sample and an inert reference in parallel. Applications of DSC. DSC can be used for all applications of conventional DTA. The advantage lies in the small size of the sample to be used in comparison to DTA. DSC essentially studied the thermal phenomenon as DTA, albeit using a different principle. Some other applications of DSC in different fields are to study glass transition, melting point, crystallization times and temperatures, heats of melting and crystallization, percent crystallinity, oxidative stabilities, composition analysis, study of heat capacity, heats of cure, completeness of cure, percent cure, purities, thermal stabilities, polymorphism, heat set temperatures, recyclates or regrinds, all can be studied with the help of DSC, whereas DTA has limited applications. So, students, today you have learned how by thermal effects, by increasing temperature, how they affect physically and chemically. Physical changes such as melting or boiling may occur at widely varying temperatures depending on the material involved, and this is a characteristic of the substance. Boiling and melting both are characteristic of a particular substance, and this is a qualitative parameter. Chemical changes such as decomposition or reaction may also take place at very different temperatures. Some are characterized, some will be estimated, some will be determined, some will be uh, quantitatively or qualitatively seen by observing the effect of temperature, and with temperature then decomposition will take place or some reaction will take place, that is the chemical changes. DTA curve in which there is an exothermic peak and endothermic peaks are obtained in DSC can be used for all applications of conventional DTA. So these thermal analysis, as I told you, is used frequently in studies of polymers for characterization of hydrated water molecules in a complex or coordination compounds, or for identification of unknown different types of materials. Thank you.